So this video is just going to go through exercise 9 and 10 on the practice paper. So in this we get a nice table and we've got to predict the structures of A, B, C or D. There is a copy of the paper attached below if you don't have it. So the key to this, although we can look at solubility in water and hexane, is look at the electrical conductivity and the boiling point. And first of all I'm going to look at the boiling point and I'm going to look for the lowest one, because covalent, giant covalent, ionic, metallic all have very high melting points and boiling points. Only simple covalent has low. So we've got our lowest one, which is B at 456 Kelvin. So this B is our simple covalent, and I've done that by looking at the boiling point. Next up, I'm going to try and find my ionic compound. Now, ionic compounds conduct electricity when they're molten or dissolved, but not when they're solid. So everything but A doesn't do this even. So they're either poor conductors or they're good conductors regardless of what state they're in. But A is a poor conductor when solid, a good conductor when aqueous. And that's ionic, because when ionics become aqueous, the ions can move and therefore it can conduct charge. So that leaves my C and my D, and that's either giant covalent or metallic. And so I know metals conduct electricity. So between C and D, D is the only one that conducts electricity. So that's metallic. And C must therefore be our final one, which is giant covalent, because it doesn't conduct electricity. Only one giant covalent compound does conduct electricity, and that's graphite. And so this clearly isn't graphite, but every other giant covalent does not conduct electricity. Part B suggests an identity for each of these compounds. So ionic, you could say it's sodium chloride, metal to non-metal. A simple covalent compound would be any molecule you can think of that is a non-metal to a non-metal. The most obvious one is probably H2O, although looking at the boiling point, probably not H2O, but we can suggest it because that is a simple covalent. Giant covalent, as I already said, could say it's diamond. We couldn't say that it's graphite. So that's the only giant covalent we couldn't suggest this is, because it doesn't conduct electricity. And then any metal, and I'll go for sodium for a metallic compound. And that would get you the marks. Obviously, lots of different answers for this. If you've named a metal here, you get the mark. Same for these two. Well, same for all three. If you've named any other ionic compound, make sure you've got a metal bonded to a non-metal for that. Any other simple covalent, so non-metals bonded together. And giant covalent, you could have had diamond, you could have had silicon dioxide. Really, they're the only two others we looked at, but there are other giant covalent compounds that can go there as well. In exercise 10, we have to predict the structure, melting point, and electrical conductivity of each of these compounds. It starts with zinc, which is a metal. So it will have a metallic lattice as its structure. So metals, we've already seen on a previous question, they form these nice little lattices. Well, I've only put pluses here. Zinc forms 2 pluses with delocalized electrons. Metals are very strong bonds. This is a strong electrostatic attraction, so it will have a high melting point. And it does conduct electricity. So yes, conducts electricity. And that's because it's got delocalized electrons that can move. If it has delocalized electrons that can move or ions that can move, then it will conduct. The next one is diamond, which I actually suggested was as an answer to a question. So diamond are giant covalent in structure. They have very high melting points. So you get away with saying high melting point, but they've got extremely high melting points. And that's because each carbon in a diamond is bonded 4 times with another with other carbons, and they're all bonded with covalent bonds, which are the strongest type of bonds. So makes it really, really strong. Doesn't conduct electricity. And that's because it has neither electrons that can move, so delocalized electrons, or ions that can move. And if it has neither of those, then it's not going to conduct electricity. Calcium chloride next, CaCl2. Now this is an ionic compound, and ions form giant ionic lattices. They have high melting points because the bonds are very strong. They conduct when molten or aqueous when they're dissolved in something. This is because the ions can move. And although it doesn't have delocalized electrons, it does have ions that can move when it's molten or aqueous. The bonds are broken, so the ions can then move. It can conduct. Doesn't conduct though when solid. So earlier on the previous question, we could identify the ionic compound because it doesn't conduct when solid, does conduct when molten or aqueous. The final one to look at in this is bromine, Br2. So bromine is a simple covalent compound. It's two bromines bonded to each other. They're both non-metals. So only thing holding it together are weak intermolecular forces. So it has a low melting point because these are very easy to break. It doesn't take a lot of energy to break intermolecular forces. It doesn't conduct electricity. And that is because it has neither electrons that can move or ions that can move. So no conducting there.